Today we begin another new topic, which is the topic of rotation of objects. So far we've only looked at what's called the translational motion of particles, and today we're going to move from particles to objects, meaning objects of some size, specifically rigid objects, objects that don't change their shape over time. And then we'll look at the rotation of those objects. And today we'll mostly focus on the kinematics of rotation, meaning just describing the way that something rotates. And we'll focus only on the rotation about a single axis, but I'll show you that, of course, rotation is a little bit more general than that. And then we'll spend the rest of the semester on rotation. So just as we did for translational motion, we'll talk about kinematics first, and then we'll move to dynamics. So what is the cause of rotational motion, or the change in rotational motion? But today, just rotational motion. So just an overview, we'll talk about translational versus rotational motion, sort of see what those mean. We'll talk about the rotational kinematic quantities, which are basically the position, velocity, and acceleration in rotational motion. We'll talk about the specific case of translational motion, so position, velocity, and acceleration of a point on a rotating object. So you can think about like a person on a merry-go-round or a bug on a rotating wheel, something like that. So there's a connection between the rotational quantities and the translational quantities. And then we'll write down the rotational kinematics equations, which follow exactly like the kinematics equations that we had for constant velocity and constant acceleration when talking about translational motion. We can do some problems with that. And finally, we'll talk about a special case of rotational kinematics, which is that of a rolling object, or another way of saying that more usually is an object that rolls without slipping. So then there's a connection between the speed at which the object moves through space and the rotational speed of the object. And we'll do an example for that. So first, let's talk about translational versus rotational motion. And I think I'm introducing the word translational right now, but it is the topic that we've been working on for the entire year. So translational simply means the motion of an object through space, as translated through space. So our problems of kinematics and dynamics have concerned like a single object that moves on some path through space, and it has some velocity, v, and there might be some acceleration. So I guess maybe the acceleration looks like this here. And we looked at both the kinematics of that object and also the dynamics, meaning how forces caused changes in that velocity, Newton's second law. This is all the concept of translational motion. The idea is that in space, we could draw, for example, a two-dimensional coordinate system. In two-dimensional space, you have the path moving through that space. Rotational motion will be separated from translational, and it will just look at an object that is fixed in space, but it is rotating, and we'll come to that in a few moments. So what is it that governs translational motion? Well, it's Newton's laws. Newton's second law in particular shows us that the sum of the forces on an object, so maybe if this is our object, maybe it only has the force of gravity, so then the sum of the forces, Fg, is equal to ma. It tells us that the acceleration of the object in space is only due to the forces on that object and its mass. This equation, though, is an equation only for the motion of a particle. So although we've applied it to objects like cars and boxes and things like that, we really meant that this was the mass of a particle, and we might say that there's no extent to that particle. So it's really just a point in space that we're talking about. That's what Newton's laws are all about, the motion of particles. So translational motion of particles is really the topic that we have been looking at for the whole semester. What I'd like to do in the next few minutes is to talk about how we can use those laws to talk about objects, so objects with some extent. And it's actually pretty simple to move from Newton's laws for particles to sort of Newton's laws for an object. And then we can immediately start to talk about rotation. So let's talk about what we mean by an object. Well, an object could be just like, for example, a meter stick. So here's an object, and you could think of that meter stick as really being a collection of particles. So maybe it's a bunch of little masses connected to each other, so we could connect them by little, maybe massless rods, something like that. So we've moved from M1, M2, M3, etc., to an object of mass M, capital M, which is equal to M1 plus M2 plus M3, etc. So how do we deal with such a system? Well, we just apply Newton's second law to every single little mass in it. So, for example, if this is an object that is only feeling the effects of gravity, then you could say, well, there's the force of gravity on M1 right here. There's also a force of gravity on M2 and on M3, etc. And then there are some other forces. They're the interaction forces. So there's a force of 2 on 1. Oops, I didn't draw that very well. Force of 2 on 1, that force. And then there's also the force of 1 on 2. And these are, of course, Newton's third law pairs. So if we were to write down Newton's second law just for one mass, we would include just these two forces. If we were to write it down for the second mass, we'd include these two. But we know that the magnitudes of these are the same because of Newton's third law, and we know that they point in opposite directions. So there's some connection between them. And in fact, what we can do is we can put all of that together. So we can write down Newton's second law for each object, and then we can sum up the entire thing. So let's try and do that. So I'm going to use that picture above as my example. We have Newton's second law for the first object, which is F net 1 is equal to M1 A1. And in this particular case, when it's only due to gravity, when it's only exposed to gravity, we have Fg1, and then we also have F2 on 1. That was the other force on it, and that's equal to M1A1. Then the next one, so that's our first object. The next object would be F net 2 is equal to M2A2, and so that would be Fg2 plus F1 on 2, and then I guess it would also have an F3 on 2, so the force of mass 3 on mass 2 as well, and then that will be equal to M2A2. So that's our second mass. So this is for M1, and this is for M2, and then of course it just keeps going. So you could add up all of these things, and what do you get? Well, you get Fg1 plus Fg2 plus, and you get the force of gravity acting on all of them. And then you have these interaction forces, F1, F2 on 1, plus F1 on 2, plus F3 on 2, plus, and then you'd also have a 2 on 3 when you get to the mass 3 equation. And you have all of those forces added together. And then finally you get all of the masses added together and all of the accelerations. So we could just write that as, for n goes from 1 to the total number of particles, mn an, like that. Well, what happens here? Well, we know from Newton's third law that these two will cancel, because we know that F1 on 2 is equal to the opposite of F2 on 1. So we can just cross those out. And then the same thing will happen for this pair, and the same thing will happen to all pairs. So you see that the internal forces between the objects will cancel out, and all that you're left with are the external forces acting on the object. So this whole sum could be written then as F external on the object is equal to, and then what can we do? Well, we could pull out m total from this thing here, and then we get mn an over m total. So I basically just multiplied by big M over big M here. And we could write this as m total of the object, and then we could just call this thing a new acceleration. And what we say is we call that the acceleration of the center of mass. And in fact, this little definition here that I've drawn here, this defines the center of mass here. So what you could write is you could write that that's actually the change in the velocity over time. So we could write, for example, that the velocity center of mass is equal to m1 v1 plus m2 v2 plus dot 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 all over the sum of all the little m's, which we could just write as capital M total. And we could go backwards one more step to look at, and this is a vector, the position of the center of mass, and that is m1 r1 plus m2 r2. So you just add up all the positions, multiplying by their masses and dividing by the total amount of mass. And so this thing here is called the center of mass. Of an object. So what does that mean? Well, up here on our picture of this rod, the center of mass would be the position where you take the position of each little object, you multiply by its mass, and then you divide by the total mass. So it's sort of an average position by mass. So where does it appear? Well, it appears like right at the center of an object that is symmetric. And if you want to look at an object that isn't symmetric, like maybe, I don't know, a baseball bat or something like that, where there's more mass up at the top than there is at the bottom, well, then you just sort of visualize where the center of mass is. And you say, okay, well, there's some mass here, and there's some mass here, and there's probably more mass up here, and therefore the center of mass will not be in the center, but it'll be somewhere offset here. So this is the position of the center of mass of an object like that. And that center of mass is given exactly by this equation here, but it's used in this equation that we've derived, which is basically Newton's second law for an object. So this is Newton 2 for an object. So no longer Newton 2 for a particle, but Newton 2 for an object. And what you can see from that expression is that, well, if you were applying gravity, for example, then gravity would be applied at the center of mass of the object. So you could effectively balance an object by, let's put the baseball bat here again. You could balance an object by holding your finger just above the center of mass. So here's your finger. You're off screen. And why does that balance an object? Well, the force of gravity would be acting effectively at that point. That's the force of gravity total on the system, and you would be balancing it with a normal force exactly at that point. So it turns out that the center of mass is the equilibrium point. It's the point at which you can balance an object. And it's the point at which it's also called the center of gravity for that reason. So although we've been applying Newton's second law to objects this entire semester, we've been talking about cars and balls and boxes sliding down ramps, we really were just using the particle equation, this equation up here, the equation for one particle, but it was perfectly fine for us to do that, to apply a particle equation to an object, because it turns out that the same thing is true for an object as long as you replace the mass with the total mass, the acceleration with the acceleration of the center of mass, and then the forces on the particle as the external forces. And of course we did that. If we were going to do a problem with a baseball bat, we wouldn't consider the forces in between each little piece of wood within the baseball bat. We would only consider the forces on the baseball bat, external to the baseball bat. So we've been basically assuming this the whole way along. So the idea is that we can think about the translational motion of an object just like a particle, and we just make the replacements that F net becomes, I guess I should write it as F net external. So the sum of the forces external to the system of particles. And then we replace m with m total, which is really just m1 plus m2 for all the particles inside, which, as I wrote before, I could write as the sum over n of mn. And then the position, velocity, and acceleration of the particle get replaced in Newton's second law with the center of mass position, the center of mass velocity, and the center of mass acceleration. And we won't really do too much with that, but you can see from the equations on the previous page, for example, this equation, that one could calculate that. For any given object, you could try to figure out what the center of mass is. And with these substitutions, you can just simply apply Newton's second law for the translational motion of an object. So what does that mean in a particular case? Well, if you stood on the ground and grabbed that meter stick, and then you threw that meter stick, but if you didn't throw it like a javelin, like if you just grabbed the end of it, maybe I should have, if you're holding it like this, and then you just throw that meter stick, well, the force that you apply to that meter stick in the beginning might be a force applied at the end of the meter stick like that. So when it leaves your hand, it might not go like a spear, it might go sort of like this. Could rotate. Something like that. So there's the meter stick going, and you think, well, that looks complicated. But what the Newton's second law for an object tells us is that the center of mass of the object, which we know for a very symmetric object is very easy to draw, the center of mass will behave exactly like a particle. And how does a particle behave? Well, a particle will go on a parabolic path. Oops, I didn't draw that very well. A particle will follow a parabolic path, just like we've seen for throwing a rock off of a cliff. So let's just summarize this. The center of mass of an object follows the path of, and we could say m total subject to F net external. So F net external, the sum of the forces of gravity on this object, is just the force of gravity on the entire object, meaning capital Mg, and it's pointing downward, and therefore the meter stick would be going through the air in its complex motion, but the center of mass of that object, the center of the meter stick, would be following exactly the parabolic path that one would find for just a baseball, like that. So the motion of an object, in terms of its translational motion, is not really all that complicated. It's exactly like the motion for a particle. But of course, the subject of today's lecture is rotation. So you can see that there's something else going on in this picture, and that is the motion of the meter stick that we didn't consider, the part where it's actually rotating about the center of mass as it moves through the air. And that's what we're going to deal with today. So where does that come in with Newton's second law? When I added up Newton's second law for all the particles, we said, well, all the internal forces cancel and all that matters are the external forces. But in fact, I could apply zero net external force to an object. So again, let's consider our meter stick. And let's say that maybe this is a meter stick we're looking down on a table on it. And let's say that I pushed it on one side so that there was a force like this. We could call that F1. Well, that would have a net force. But if I pushed it on another side, with exactly the same magnitude but opposite direction, well, F1 plus F2 as vectors would be equal to 0. So 0 net force. But you know that if you did that to a meter stick, it's not like the meter stick would not move. If it started out with 0 velocity on the table, well, Newton's second law for an object, as we just saw above, would mean that its center of mass will not move. So its center of mass will remain right there. But what's going to happen to the meter stick is it's going to start to rotate. And we draw that with something called the Greek letter omega. So this is omega. And we call it a rotational velocity. So by applying these forces like this, we went from omega is equal to 0 to some omega greater than 0. And we draw that as this rotational thing, which we can draw with sort of curved arrows here. So these aren't vectors, these are just arrows meant to show that the object is rotating. So Newton's second law for an object that we just derived above is not really the whole story for the object. We've in some sense thrown out a bunch of information about the motion of each of these little particles within here because we threw out their interaction forces, but there's still some motion of the object going on even if its center of mass is not moving. So I guess I should write that clearly. V center of mass is still equal to 0 here, but it does have some rotational velocity. And that's what we're going to try and characterize today. So for the rest of the semester, we're going to talk about this kind of rotation, and we call this a rotation about a single axis. So the idea is you're looking down on a table at, we could call that the XY plane of the table, and then this little dot that I've drawn at the center of mass, I'm going to call the axis of rotation. And what do I mean by that? Well, it's really the z-axis. So it's the z-axis coming out at us. So we could even call it the z-axis. And we'll actually label some of our quantities with little z's because we're talking about rotation about the z-axis. So we'll talk only about objects that rotate about a single axis. We'll almost always think about that axis as this point here, meaning as a point, as an axis that comes out of the page at us. So rotation about that. You could take a piece of paper, put your finger on the center of the paper, and then rotate the paper. Your finger is then the z-axis. But that kind of rotation is actually just one very specific case of the generic rotation of an object. So we might just take a quick moment to look at what an object could do in general. Well, if I had a ping pong paddle, so I'm just going to draw a ping pong paddle because it's sort of easy to draw and it's not completely symmetric. I could choose an axis about which to rotate it. So I could choose this as my axis and then say, okay, I'm going to rotate it about this axis. So at some later moment, it might look like this, like that. So I can rotate the ping pong paddle about that axis. Rotation about a single axis. But that's not the only axis that I could rotate about. That's the z-axis. Well, I could also rotate it about the x-axis. So let's try and draw that. So here's my x-axis. If that was my z-axis, then this is my x-axis. So what does rotation look like for that? Well, it means that I'm going to be taking the object and sort of pushing the top of it back into the page and pulling the bottom of it, the handle, up out of the page. So at some later moment, it might look like, I don't know if I'm going to be able to draw this very well, something like that. I think I drew it wrong, didn't I? The handle is too, the axis was not going through the handle there. So it's more like this. That's all right. So that's another way that it could rotate. And then there's a third way. Do you see which way that is? So it should be the y-axis. So here's our ping pong paddle, and then we can draw the y-axis there. And if we're going to rotate about the y-axis, then that means it's going to go like this. And so the ping pong paddle would then at some later moment look like that there. So it's sort of, we're twisting the right side down into the page and the left side out of the page, and it's rotating about that axis. So the generic motion, the generic rotational motion of an object is that it could rotate about any three axes in three-dimensional space, and in fact it could do all of them at the same time. So you could try this with a ping pong paddle. You could just sort of like throw it across the room and try and give it some generic rotation, and you'll see that it rotates about all three of these possible axes. That is a very complicated process, and it takes a little bit more math than we have in order to describe that carefully. So we're going to focus only on this case up here. We're going to focus only on the case of rotation about a single axis. We'll call it the z-axis so that we can think of the page as the xy plane. And we'll talk carefully about that kind of motion. Okay, so let's talk about rotation. So we're going to define the rotational kinematic quantities in analogy to the rotational quantities. So I've already written down what their names are effectively. They are the position, the velocity, and the acceleration. But they're going to be the rotational position, the rotational velocity, and the rotational acceleration. So what are they? Well, in translational motion, we have the position of an object we called the r vector, and that was, if you remember, if we draw like an x, y axis, it could be, for example, the x position of a car as it's driving along the axis, so maybe it's just the x position, but it could also be, for example, the two-dimensional position, meaning the r vector of a bird in space. So we think about the position of an object in that way, either the position along an axis or a vector in two-dimensional space, or of course you can talk about the x component of that bird and the y component of its position. That's translational position because in each case these objects are moving through two-dimensional space. They have translational motion. So what is the equivalent for rotational motion? Well, let's draw ourselves some sort of object to rotate, and I don't want to take something symmetric, so let's again use the ping pong paddle. So here's an object, and then we choose a point on it to be our rotational axis. So I guess I'll just choose this point here. So if I rotate about that axis, then I could draw it at a different moment in time. So it's like a little more than halfway up the handle. So at a different moment in time, it will look like this, something like that. Well, the way that I describe its rotational position is by drawing a line here and showing myself the rotational distance that it has traveled, which is, of course, the angle. So the rotational position of an object that is rotating about a single axis is what we call the angle of the object. And it's the angle relative to some position. It could be relative to its initial orientation, or it could be relative to some other axis that we define. But the angle is the key quantity. It's the positional vector. It's the positional quantity for rotation about a single axis. You can imagine that if we had these more complicated things, there would be an angle for the z-axis, there would be an angle for the x-axis, and an angle for the y-axis, and that's why things start to get very complicated quickly. Just like there's a position of the bird in two-dimensional space, you could do the same thing. But we're not going to do that. We're only going to look at a single angle, which is the rotation about the z-axis. So let me just remind you, this is the axis of rotation. So what are the units of angle? Well, you think about it in degrees, but what we're going to focus on at this point are radians. So let me just remind you what a radian is. 360 degrees is called 2 pi radians, or you could also use 180 degrees is pi radians. So that's the definition of a radian. And you could convert, so for example, if you had like 40 degrees, how do you convert that to radians? Well, that's going to be equal to 40 degrees times, and then you divide by 180 and multiply by pi. And what is that? I don't know what that is. Let me calculate it. So 40 times pi divided by 180 is 0.698 radians. There. So radians, they go from 0 to 2 pi. And remember, pi is about 3, so 2 pi is about 6. So going a quarter of the way around is 90 degrees. That will be a little bit more than 1 radian. Okay, so that's the rotational position, which we call the angle. Maybe I should highlight that a little bit more here. So, angle. Then we move to rotational velocity. And let me remind you about translational velocity. So translational velocity of an object like a car well, that was found as this vector. And we found that v sub x was equal to delta x over delta t. So the v vector is delta position over delta t. In the x direction, it's just delta x over delta t. If we had the bird, then our position vector looks like this, but the change in the position vector will be pointing along the path. So at some later moment, its position might be over here, and therefore its velocity vector points like that. And that's going to be equal to the change in the position vector over the change in time. So that's the translational velocity of an object, the velocity of an object as it moves through space. So what's the rotational quantity? Well, let's draw our ping pong paddle again. So we have an object that is at this position, angular position at one moment, and it is at this position at a next moment. And so if we use our definition of translational velocity to define rotational velocity, then we would say that the rotational velocity is delta angular position over delta t. So what does that mean? It means that if it's over here at t is equal to 0, and it's over here at t is equal to delta t, and it travels an angular position of delta theta, our rotational velocity is defined as this equation. And that thing, as we called it, omega, is called the angular velocity. So you see that the equation is very similar to the one that we have for the one-dimensional translational velocity. It's just the one-dimensional position difference over difference in time. And you might say this is actually omega z, because it's the angular velocity about the z-axis, the axis that points perpendicular to the page. So that is our angular velocity. We should mention a few other quantities related to this angular velocity. So if we wanted to, we could talk about the period of motion. So imagine that this ping pong paddle is rotating about this z-axis, but it comes back to the top again over some period. So the period of motion, and we'll assume a constant angular velocity. We write that as t here. And so what does that mean? Well, it means that we can write omega is equal to the total angular distance traveled around divided by the total time traveled, which for a full circuit would be 2 pi all the way around divided by the period. So we can say that omega is equal to 2 pi over the period for an object that is rotating with constant angular velocity. So it's a relationship between the period of rotation and this angular velocity. And for that reason, we also call it the angular frequency. So it's also called angular frequency. And why do we call it the angular frequency? Well, the frequency what does the frequency mean? It means the number of rotations per time. And that thing, which we can call f, is just equal to 1 over the period. And you can see why that's the case. If I say that this ping pong paddle takes 1 minute to go around, then the frequency would be 1 rotation per 1 minute. Or if it takes half a minute to go around, then the frequency would be 2 rotations per minute, right? So if that's the case, if frequency is equal to 1 over t, well then, because t is equal to 2 pi over omega, if I just do algebra on that equation, then I can write this as 1 over 2 pi over omega, and I get omega over 2 pi for this equation, or I can write that as omega is equal to 2 pi times f. So we have a few equations that we have here. One is omega is 2 pi over t, which is the same as t is 2 pi over omega. And we also have omega is equal to 2 pi over f, which is the expression of omega as an angular frequency. And these are really only for the case of constant angular velocity, because if the angular velocity is changing, then you can't say that there's a constant period of motion anymore. If it's speeding up in its rotation, then the amount of time it takes to go around the first time will be different, will be longer than the amount of time it takes to go around the second time. But it's good to have this sense about how the angular frequency relates to the period of motion and the frequency. The angular velocity relates to the period of motion and the frequency. So we have one last kinematic quantity, and that's the acceleration. And we know from translational motion that the acceleration in the x direction is the change in the velocity in the x direction over the change in time. So it's the change in velocity over change in time. Well, for our ping pong paddle, let's just draw out what that means. At some moment, it's at this position. At the next moment, it's at this position. And now instead of just drawing the positions, well, what would the picture be for the translational motion? That's like if we have an object that's driving, maybe a car driving on a circle. We have a final velocity, and we have an initial velocity, and acceleration is the change in those velocities divided by the change in time. So we need to look at the initial angular velocity and the final angular velocity between two moments in time. So what is that? Well, that will be delta omega over delta t. That's final minus initial. And we have a name for that, which is alpha. And this is called the angular acceleration. So you see it's almost exactly the same equation, it's just with our new quantities. We have some new variable names. So this thing is the Greek letter alpha. This one is the Greek letter omega. Here. and that's our angular acceleration. So in a moment we'll talk about the constant velocity and constant acceleration kinematics, and we'll be able to write down equations with theta, omega, and alpha, just like we did for x, vx, and ax. Before we do that, we want to talk about something else, which is how to connect the translational motion of a point on a rotating object to the rotational motion of that object itself. So the idea here is to consider like a bug on a rotating object. And it doesn't really matter what the shape of the object is that's rotating. If it rotates about a single object, then that bug's path will be the same. So let's just draw some weirdly shaped object. I don't know, maybe there's some weird thing like this. It's going to be very hard for me to draw that a second time. We'll assume that it's going to be rotating about some axis. And then we can place a bug on it at some random position. How about here? There's our bug. And then we can consider what happens when that thing starts to rotate. So, oh geez, I have no idea how I'm going to draw this again. Let's try it. So we have, well, I can copy it to give us our initial point. So this is what it looks like initially. And then at some later moment, the object is going to look like this. Well, it's going to be like something like that. And where did the bug go? Well, the bug went from its original position to its new position, right there. So what was the motion of the bug? Well, you can see that the bug just travels on a circle. So regardless of the shape of the object, because the bug's radius from the axis, which we can call r, does not change, and that's because it's a rigid object, the bug's position relative to the axis is always the radial distance, and therefore it always travels on a circle. So when we think about the translational motion of a point on a rotating object, well, we think about that as circular motion. So the bug's path is going to be a circle, and it's going to have a velocity and an acceleration which correspond to that circular motion. So what we're really going to be doing right now is considering a little bit more generally the case of circular motion, which we already covered a few weeks ago. So let's do it one by one, the displacement and the velocity and the acceleration of that bug. So what is the displacement of the bug? Well, we have the circular motion, so whatever the object is, that bug is traveling on a circle. And so let's just draw some. So here's our bug. It's out at a certain radius from the axis of rotation, and then let's just draw some little object here that it's sitting on. Now that object is going to move over here, and the bug will then be at this point here. So what is its displacement? What is its angular displacement, and what is its translational displacement? Well, its translational displacement is the length along the arc. We call that the arc length. And its rotational displacement is the angle that it has traveled. So how are those things related? That's our goal, is to relate the translation of the bug through space to the rotational quantities. Well, we've already looked at this, at how do you relate an arc to an angle. So this is the picture that we're thinking of. And the way that you know that is that you know exactly what the answer is for a full circle. So you know that for a circle, the circumference is 2 pi times r, but that's just equal to the total angle around multiplied by the radius, and that would be, you could call it S total. So the equation that relates S, R, and theta is just S is equal to theta times R, as long as you write the angle in radians. So this equation is always true for an arc length and a circular path. So that's the relationship between the translational position, s, and the rotational position, theta. What about velocity? Well, let's draw our circle again. So we have the bug. At one moment it's here. At the next moment it's here. And we're wondering, how do you relate? Actually, let's put it a little bit closer together. Let's just consider a shorter distance traveled. So we're wondering, how do you relate the change in the angular position to the change in the translational position, delta s? Well, delta s, the velocity of the object, so the velocity vector of the bug through space, its translational velocity, its speed is given by the distance traveled over the time traveled. And in this case, the distance traveled is just delta s, and the time traveled we could just call delta t. Well, we already know, though, the relationship between delta s and delta theta. We see from this picture and from the equation above, this equation, that delta s is equal to r delta theta. So this equation I could write as delta r theta. So what does that mean? Well, the radius is constant here. That doesn't change over time. So when I say the change in r times theta, I really just mean r times the change in theta. So that tells me that v, the translational speed of the object on that circle, is equal to r times omega. Delta theta over delta t, that was our definition of the angular velocity. So the translational velocity, the translational speed of an object traveling on that rotating, of a point traveling on that rotating object, is given by the rotational velocity multiplied by the radius from the axis on that object. So you always have to consider what that axis is, the distance to the axis. So let's do an example of that. So if we have a Ferris wheel that spins once per minute and it has a 25-meter radius, then what are the angular and translational velocities of the passengers? So here's a passenger here. And we can sort of sketch out what we mean by translational and rotational velocities. So this is rotation about this axis here. And therefore I could draw this as sort of a rotational velocity that looks like this here. It's rotating, let's say, clockwise. The translational velocity of the person, of the passenger at any moment, is tangent to the path. So I just draw a velocity vector that looks like this, v. So what are those things and how are they related? Well, the information that was given was once per minute. And that is, if you remember from the definitions above, that's a frequency, the number of times that it goes around per time. So we can write this as the frequency of the wheel is equal to 1 over 1 minute. That's the frequency. Let's put that in SI units. So that's 1 over 60 seconds. And then we can use our equation that the period is equal to 1 over the frequency. So the period is just equal to 60 seconds. Why do we find the period? Well, because if this thing is moving with constant angular velocity, then that means we can write omega as equal to 2 pi over the period. So that angular velocity is also called the angular frequency. It's equal to 2 pi over the period, and so we can calculate it. So let's do that. We have 2 pi divided by 60 seconds, and we get 0.105, and that thing will be in radians per second. So that's the angular velocity of the Ferris wheel. Well, what is the translational velocity? So what is v? What is the speed of that passenger as they move along that circle? Well, we just figured out what the equation is, what the relationship is. So the translational speed v is r times omega. So that's going to be 25 meters times 2 pi over t, or times 0.105 radians per second. And what we get is 2.6 meters per second. So the speed through space is 2.6 meters per second. The rotational speed, the speed at which it is rotating, is 0.105 radians per second. Continuing on through our, remember what we were doing here, we're comparing translational motion of a point to the rotation of the object. So we have one left to do, which is the acceleration. But in fact, we've almost finished this already, because we've already talked about circular motion and the acceleration of objects in circular motion. So we found in particular that if you have, for example, a bug which is traveling on a circle about the center of that circle, which we could call the axis, then its acceleration, well, if it has constant speed along the circle, its acceleration is v squared over r. That's the magnitude. But regardless of whether the motion has constant velocity or not, we know that the component of the acceleration, so maybe we can make this faster later, so the bug is speeding up, we know that the acceleration will have a component in the radial direction, which is a sub r, and a sub r is always equal to minus v squared over r. So we already know what one of the components of the translational acceleration is for an object that moves on a circle, which in this case is an object which is sitting on a rotating object. So that's one component. But what about the other one? What about the tangential component? How do we find that? Well, the tangential component is really just the acceleration along the path. So along that circular path, we have some initial velocity here, and then we have some final velocity here. And we could talk about the change in the speed of that object. So the tangential is really just the change in the speed of that object over the change in time. And what is that? Well, we already found that the speed of the object on the rotational path is given by r times omega. So I can write this as r times omega over delta t. Again, r is a constant over that path. It stays on that circular path, so r is constant. This is r. So I can write this as r times delta omega over delta t, which tells me that the tangential component of the acceleration, meaning the change in speed along the path, is just equal to r times alpha. So this is the new part that we get from our rotational motion, is that if we know the angular acceleration, then the translational tangential acceleration is given by that value times r. So the entire acceleration vector then, the translational acceleration is equal to that pair of components, AR, AT, and we know that AR is minus v squared over r, and at is r times alpha. And in fact, we could write that completely in terms of rotational quantities, because we know that v, the speed, is equal to r times omega, right? So we could write a, which is ar at, as minus, well, this is going to be r squared omega squared over r, like that, and then we can cancel those out, so we get minus omega squared r alpha, like that. So we can write the translational acceleration of a bug sitting on a rotating object. So here's our rotating object, here's our axis, and here's our bug. It will be traveling on a circular path. If it turns out that it is not only rotating, but also accelerating in its rotation, then the acceleration vector of that bug will point partly inward and partly forward. So it will point something like this. A. So this is the radial axis. The acceleration vector has an inward radial component. That's the minus v squared over r part. And here's the tangential axis. And it will have a positive tangential component because the alpha is positive, because it's accelerating as it rotates. So we've compared now the translational motion of a point on an object to the rotational motion of that object as a whole. So if you know how a rigid object is rotating, then you can figure out the translational motion of any point on that object just by using the distance to the axis. And that distance to the axis is what we're calling the r, the radius here. Okay, so now let's write down the equations for rotational kinematics. And when I say kinematics, we've really been talking about kinematics the entire lecture. We've been defining position, velocity, and acceleration for rotation. That's what kinematics means. But if you remember what we talked about at the beginning of the semester, we had specific equations for the special cases of constant velocity and constant acceleration. So we can do exactly the same thing here. So if we look at constant velocity, well, that was that the velocity in the x direction was just equal to a constant. So the velocity of the x direction of a car was just equal to its velocity at its initial moment in time, v0x. And what did that imply? It implied that the position of the object was equal to the initial position plus that velocity times time. So what does that mean for constant angular velocity? Well, if omega is constant, so omega, and let's write it as omega z, because remember, let me remind you, we have an object that looks like this. We have an axis, and that axis can be thought of as pointing out of the page. So if this is x and y, then the axis is actually the z-axis. And then the omega, we can call omega z because it's the omega around the z-axis. So for constant angular velocity, we say that omega z is just constant. So it's equal to omega naught z. It's always equal to the same value. Well, what does that imply for the position? Exactly the same thing. Theta is equal to theta naught plus omega naught z times t. So I'm just writing it down exactly based on this equation here. And the reason I can do that is because the definitions are exactly the same. So I'll just say this once. Vx is delta x over delta t. That's what gave us this equation. And here we have omega z is equal to delta theta over delta t. So the same equation gives us the same definition of the velocity gives us the same equation. So this is an equation that we can use for kinematics. Let's put a box around it. and you'll find it on your equation sheet. And then we have constant acceleration, constant angular acceleration. So if you remember for translational, that just means the acceleration at any moment in time is equal to the initial. And that meant that the velocity in that direction was increasing linearly with time. And that meant that the position looked like this. The position depended quadratically on time. The same thing is exactly true in the constant angular acceleration case. So the angular acceleration with respect to the z-axis is just equal to the initial value. So it's not changing. If that's true, then omega z is changing, and it's changing linearly with time. And if that's true, then the angular position changes quadratically. So we have these equations for constant angular acceleration. And we'll solve some problems with that. So let's do an example. A power saw, so this is like a circular cutting saw, it's spinning at 500 RPMs. RPMs means rotations per minute, so that's actually an expression for the frequency. A power failure occurs, and the power is off for 30 seconds, during which time the saw slows down uniformly. So that means a uniform acceleration, a uniform rotational acceleration, and that's because of the friction in its bearings. So while the power is off, the saw makes 200 revolutions. How fast is the saw spinning when the power returns, and how long would it have taken for the saw to stop if it had continued to decelerate? And how many revolutions would it make in that case? So we're given a constant angular acceleration. So maybe we should write that down. Constant angular acceleration. Alpha z is equal to alpha naught z. But we were not told exactly what that value is. So it's actually unknown what that angular acceleration is. It's just known that we can apply the equations of constant acceleration. So let's do them using some of the information that we do have. Well, what do we know? We know that it has an initial angular velocity given by 500 RPMs. So let's write that as an initial frequency, 500 revolutions per minute. And we could write that in SI units. So that's 500 revolutions per minute times 1 minute over 60 seconds. So what is that? Well, it's 50 divided by 6. I don't know what that is. 8.3. That's how fast the saw is spinning, 8.3 revolutions per second. Now we could convert that to an initial angular velocity, and that equation is done by that angular frequency equation. So you could do it through the period if you wanted to, or you could just write it as 2 pi f. So if it's going around 8.3 revolutions per second, then if you multiply that by 2 pi, then you find out how many angles per second it's going through. So 2 pi f, well, let's just write that down. 2 times pi times 8.3 is 52.36 radians per second. So that is our initial angular velocity, and let's use that z there. So omega naught z here. So what does the picture look like? We have a saw. This is the cutting edge of the saw. It has some axis, like that, and it's going to be rotating with some omega, which is changing in time, but it has some initial angular velocity, which is equal to 52 radians per second. So we know that it doesn't stop after 30 seconds, but we know that in 30 seconds it makes 200 revolutions. So what does that tell us? Well, that's an expression for the angle that it passes through. So what we could do is we could write down the equation for the angular change over time under constant acceleration. And that equation was theta is equal to theta naught plus omega naught z t plus 1/2 alpha naught z t squared. And we could write that as delta theta, so just subtract off theta naught from both sides, is equal to omega zt plus 1/2 alpha naught z t squared. Delta theta is exactly what we were given, 200 revolutions. Well, that means that it's going to be 200 revolutions times 2 pi. So we will be able to plug that in. Maybe I can write that here. So delta theta is equal to 200 revolutions times 2 pi radians per 1 revolution. So it's going to be something like 6 times 200, about 1200 radians. That's what delta theta is. Let's not plug it in yet, but instead let's plug in what we have. So omega is, I drew it as something that is a clockwise rotation here, but we know that the saw is decelerating. So when I draw the alpha, I really want to draw it backwards. So there's going to be an alpha like this, and that alpha has the same value at all times. So it's some constant which is unknown. And I draw it backwards because it's decelerating, because omega is getting smaller and smaller. So when I plug into this equation, we do it the same way that we've done before. Well, I'm going to plug in omega naught z as, let's just call it omega naught. My t is known. That's the amount of time that the power is off. And then I have plus 1/2, and my alpha is going to be minus alpha naught. So let's call this alpha naught here. And my t is again t off. So there's my equation. What is unknown here? Well, I don't know what alpha is, but I do know what everything else is. So I should be able to solve for alpha. So let's do that. So we have 1/2 alpha naught t off squared is equal to omega naught t off minus delta theta, which tells me that 2 times omega naught t off minus delta theta divided by t off squared is equal to alpha naught. So I should be able to plug that into my calculator now. So we have 2 times parentheses omega naught we found as 52.36. Multiply that by t off. So t off was given as 30 seconds. That was given in the problem. So times 30. Then I subtract off the total number of radians that it went through. So delta theta we found is 200 revolutions times 2 pi, because you get 2 pi radians for every revolution. Close parentheses and divide by t off squared, so 30 squared. And we find that theta naught is equal to 0.698. And what are the units for alpha naught? Sorry, not theta naught, alpha naught. Those are radians per second squared. Okay. So that is our alpha naught. That's not what we were asked, is it? It says, how fast is the saw spinning when the power returns? Well, we found something, but we didn't yet find what we want. How fast is the saw spinning? Well, that's an omega final question. So we use our omega over time equation for constant acceleration. So there's our basic equation. So omega z will be omega final. Omega naught z will be omega naught. And alpha, again, it points in the opposite direction to omega, so I'm going to call that negative. And then t is t off. And this is just an equation that we have now for omega final. So omega naught we were given as 52.36, so we found it as that. We subtract off the acceleration that we just found, 0.698, as multiplied by 30 seconds. And we get 31.42 radians per second. So there's the answer to part A. Part B, I might need some more space. So part B says, how long would it have taken for the saw to stop, and how many revolutions would it make? Well, now t is an unknown, but we know what our omega final is. So we can use the same equation again. Because we know what the angular acceleration is, we just don't know the amount of time. But we do know that the final we're assuming to be 0. So we have omega naught minus alpha naught t stop. That's our equation. So t stop is equal to omega naught divided by alpha naught. And we can just plug that in. So we have 52.36 for omega naught. We divide it by alpha naught, which we found to be 0.698. And we get 75 seconds. So the radians cancel out, and the units are seconds. That's how long it takes to stop. How much angle would it go through in that amount of time? Well, we can again use exactly this equation. So we have delta theta total is equal to omega naught t stop now minus 1/2 alpha naught t stop squared. So what is that going to be? Plug it in. Omega naught is 52.36. Multiply it by the amount of time we just found, 75 seconds. And subtract off 1/2 times alpha naught, which was 0.698, multiplied by t stop squared. And we find 1964 radians. So the amount of radians it went through when the power was off was given by this equation. Remember, that's 6 times 200, so about 1200 radians. It went through another about 750 radians if you would let it go to a stop. There. Okay. Last topic is the special case of kinematics of a rolling object. And as you'll see in a few minutes, this is called rolling without slipping, because it's important that the object rolls along a smooth surface, but that it does not slide. There's no slipping there. And this will be the case for something like the tire on your car. When you drive your car, your tire rolls exactly along the road, and it does not slide there, one hopes. Because if it does, then you're going to have friction between the tires and the road. You're going to lose energy there, and you're also going to burn the rubber off your tires. So let's try and draw this out. So if we have a circle, and this could be a circle, but it could also be anything with a circular cross-section, like a sphere or a cylinder, something like that, or a hoop. And I'm just going to put a marker on that circle that shows where one position is at some moment in time. So I'm going to call this my t initial moment in time here. And at that moment, the marker is pointing directly down to the ground. Now, at some time later, my circle will be a little bit further along. I think I increased its size, didn't I? Let's make it a little bit smaller. That's about right. A little bit bigger. Oh, geez. So where's the marker going to be on the circle if it has rolled in that direction? Well, the rolling means that it has some angular velocity, like that, and I guess it'll still have some angular velocity, like this. We'll assume that that remains constant. The fact that it's moving to the right means that it has some translational velocity as well, and we're going to call that the velocity of the center of mass. So the center of mass of a circular object like that would just be the center of the object. And we'll call the omega about the center of mass. Meaning if you just walked along with the wheel as it rotated, you would see this arrow, this marker arrow, rotating around and around and around. So we'll separate out the motion into the motion along the road, v center of mass, and the motion around its center, the omega center of mass, and we'll see how those are connected. But where does this arrow go as it rotates there? Well, it goes exactly as far along the edge as this distance. So this is some distance here, which we could call delta x, like that. And how long is that distance? Well, it's going to be exactly the same length along the edge here. So do you understand what I'm doing here? The arrow should be pointing up and to the left because the object has rolled through exactly the same distance along the ground as it did along the edge. Well, what does that mean? It means that in the time that it went through delta x along the ground, it went through a delta theta in angle, and it went through a delta s along the arc length of the circle, like that. So you can see that the theta, the s, and the delta x are connected. So how are they connected? Well, delta s is exactly equal to delta x. And that's true as long as the object is rolling without slipping. You can see why slipping would be a problem. If it turns out that the wheel slips a little bit, well, the worst case scenario is that the wheel simply goes around, meaning the arrow goes around, but it does not move. So this is like if you're in your car and you keep your foot on the brake, but then also put your foot on the gas. Your wheels spin around in one place, but the wheel does not move. In that case, your delta x would be 0. You would not move the wheel, but your delta s would be large because the wheel would be spinning. So that's why we consider only the case of rolling without slipping, where these things are connected. Well, we know what delta s is. Delta s is equal to the radius of the wheel multiplied by delta theta. So we can relate the position change of the wheel to the angular change of the wheel. And ultimately, what we'd want to do is to figure out the relationship between omega and v, so we just divide this equation by delta t. So what do we find? We find that r, omega about center of mass, is equal to v of center of mass. So when an object rolls without slipping, the translational speed of that object through space, that's this rightward pointing velocity vector here, is related to the rotational speed of the object about its center of mass by exactly this equation. And if you remember, that was exactly the same equation that related a point on the edge of an object to the rotation of the object. So it's easy to remember in that way, but it's a different it's a different reason for that relationship, and it's actually different quantities. So let's do one more example. A car with 18-inch diameter wheels gets on the highway, speeds up to 75, and then gets off 10.5 miles later. How many times did one wheel go around? What was the maximum angular velocity relative to an axis through its center? So this is exactly how the odometer on your car works. The odometer in your car doesn't measure the distance that you've traveled. It simply measures the number of times that your wheels have gone around. It can count the number of times your wheels goes around, and it knows the diameter of your wheel, so it knows the circumference, so it knows exactly how far it has traveled. So the idea is the wheel is a circle, and that circle will travel a certain distance to go around once, and that distance traveled should be exactly the circumference. So what is the circumference here? It's something like, so that means it's going to go like that. So the wheel will be over here, because this distance here, delta x, is equal to 2 pi r. So it's marked exactly like that and exactly like that, where that's the radius. So the wheel goes around with some omega, and it kisses the road all the way along, and in one revolution it goes exactly a distance of the circumference of the wheel. So how do we relate these things? Well, if we're told that you travel a distance, if delta x is equal to 10.5 miles, well, let's convert that to SI units. So 10.5 miles, this is the Roadrunner's conversion. A 6.2 mile race is 10.0 kilometers. And then 1 kilometer is 1,000 meters. So what is miles in meters? So 10.5 times 10 times 1,000 divided by 6.2 is about 17,000 meters there, or 17 kilometers. Approximately. So we've gone 17,000 meters. So how many times did the wheels go around? Well, the circumference of the wheel is equal to 2 pi times r. So that's 2 pi times r was 9 inches. But let's convert that to SI as well. So we have 2.54 inches per 1 centimeter, and we have 100 centimeters per 1 meter. So what does this turn out to be? It's 2 pi times 9 divided by 2.54 and divided by 100, and that is 0.223 meters. So the number of rotations is going to be equal to delta x over c wheel. So this is 1 rotation. You go around once, so at some point in the middle the arrow is pointing upward like that. Well, how many rotations does it take to go a certain distance? Well, you just divide by the distance by the total by the circumference of the wheel. So what is that? It is, I'll use my exact answer, which is something like 16,900 and divide by 0.2226, so it's 76,000. So about 76,000 times around in order to drive 10 miles. And your odometer just counts what that is. It adds in 22 centimeters every time your wheel goes around. 22, that sounds wrong. If it's 9 inches. D. Seems like that's wrong. Is that wrong? Let me check. So we said the diameter is 18 inches. We have a radius of 9 inches. So 2 pi times the radius is the circumference. So it's 2 times pi times 9. And then we divide by 2.454. Oh, that's what I did wrong. Sorry. Good thing I have some sense. So 1 inch is equal to 2.54 centimeters. That's the problem. So its circumference is not 22 centimeters. What is it? Well, it's going to be 2 pi times 9 times 2.54 and divided by 100. And that's 1.44. That's better. So it's longer than a meter, the circumference of your wheel, and therefore it's going to be smaller than 76,000. It's going to be 17,000 divided by 1.44 meters, so it's approximately 12,000 times around there. Okay, what is the maximum angular velocity relative to an axis through its center? So we're looking for omega max, and we know the relationship then, so this was part A. Part B, we want to know what omega max is, and that's omega max of, so omega max about the center of mass. So what's the angular velocity about the center of mass? Well, we just found an equation for that. It's equal to r times v max of the center of mass. So if we know what the maximum speed of the wheel is, so here's the wheel of your tire, and it's going along with some v center of mass, well, that's exactly the speed of your car. Then we can figure out what omega is for that thing. Well, that's just the radius of the wheel, so that's going to be 9 inches. We got to do that conversion again. And then we multiply by the speed, the maximum speed, which we were told was 75 miles per hour. And then we want to convert that. So that's going to be 6.2 miles over 10 kilometers. 1 kilometer, 1,000 meters. So what does that turn out to be? So we have 9 times 2.54 divided by 100, and then multiplied by 75, multiplied by 10, divide by 6.2, and multiply by 1,000. And we find about 27,650 radians per second. So the angular speed of your wheels as you're driving along at 75 miles per hour is about 28,000 radians per second, or if you divide that by 2 pi, it's about 4,400 revolutions per second. That's the actual frequency. So omega would be the angular frequency, and 4,400 revolutions would be the actual frequency. That also seems high. Well, you check, see if that's correct or if I made a mistake. So we'll continue with rotation next time. We'll talk about rotational energy and how we can apply conservation of energy techniques for rolling objects. And this connection between a rolling object and its translational velocity will be important in that context. I'll see you then.